What does the CPU do? We now see that it performs elementary operations at a certain level of abstraction.
We will describe such simple instructions. However, many times, a few common instructions are grouped as a macro, and at the assembly language level, they constitute an abstraction.
Programmers using assembly consider macros as a single instruction, but in effect, the CPU performs 2 or 3 instructions.
The first basic operations move data from the main memory into the registers.
These are usually named load operations.
If we illustrate them with MIPS, there are different types according to the data type brought into the register.
Those instructions that load a byte use a 32-bit address to indicate a byte in memory to bring only 8 bits into the rightmost byte of a register.
In this case, the other 24 bits of the register are 0.
However, those instructions that load a word require an address divisible by 4. The address is the position in the main memory, where to bring 32 bits into a register.
While these operations always bring bits seen as a value from memory, from the assembly perspective, we sometimes retrieve an address, which in the assembly code is a label.
Symmetric operations also store data out of the CPU registers into a position in memory.
Again, the MIPS assembly language offers versions according to whether a byte, a half word or a full 32-bit word is copied from the indicated register in the instruction out to the memory.
The second type of operation we typically find is arithmetic operations.
In the case of the MIPS, the most basic instructions consist of indicating 2 registers as the operands and 1 destination register for the result.
Thus, an operation such as add $T1, $T2, $T3 means that the content of register T2 will be forwarded to the ALU as well as the content of T3.
These two 32-bit values will be taken as signed integers in complement 2, and after completion of the addition, the result is placed in the destination register, in this case, T1.
The MIPS add generates an exception if there is an arithmetic overflow in the 32-bit representation.
The MIPS instructions for arithmetic sums and subtractions have a version where values are considered and signed, and no exception is generated if overflow happens.
The issue of an exception is not so important here, but for clarification, an exception usually implies the regular flow of the program to the next instruction is interrupted.
The next type of simple operation is one that shifts the pattern of zeros and ones in a word to the left or the right.
The shift operations result in multiplication by a power of 2 or division by a power of 2 of the value represented by the affected operand.
For example, SLL stands for shift left logical. When followed by $T1, $T1, and 3, the value in T1 is multiplied by 8.
While shifting has arithmetic effects corresponding to multiplication or division, it also has logical effects when the leftmost bit is not considered the sign but part of the entire pattern.
Typical logical operations are performed bitwise on operands.
For example, when inverting each bit, this negation, in the case of MIPS assembly, is named NOT, and negates bitwise a source register with the result placed on a destination register.
Other common logical operations are the bitwise AND and the bitwise OR, but these are binary, taking 2 operand registers and a destination register.
The effect is the bitwise application of Boolean logic, taking a 1 to mean true and a 0 to mean false.
The summary of what a CPU does may leave you wondering how something that does so little has made possible so powerful tools and amazing machines of our current digital era.
So far, we have not mentioned those instructions that change where the program goes for the next instruction.
Without the ability to making decisions, computers would be mere calculators.
Nevertheless, another aspect that leverages simple operations into the amazing power of modern computers comes from packaging the technology into levels of abstraction.
Moreover, at the level of the CPU, things happen super fast.
On the other hand, if you ever study Turing machines and review what a von Neumann CPU does, you should conclude that the Turing machine is a suitable model of our physical devices for computation.